Swayam Prabha. Digital India. Educated India.
Friends, let us continue our discussion on design equations for ideal reactors. But before we continue, I just want to once again reiterate what is ideal reactor. The reactor ideality is determined by the conditions of flow inside the reactor, and it has nothing to do with what size, shape or color that reactor or material for that matter that reactor is made up of. So, it all depends on what kind of flow is going through the reactor or what flow conditions exist in the reactor. So, we have two extremes of flow conditions, ideal flow conditions. One in which we have a good way of mixing the entire contents of the reactor, so that there are no heterogeneity in the reactor, or in other words the reactant concentrations, temperature or any other condition that matters for the reaction are uniform throughout the reactor. Just imagine the room in which you are sitting right now as your reactor, and if you look at the right corner, left corner, middle, top, bottom, anywhere you look, if the conditions are same, that is, this room is your reactor and concentrations of various species are same, for example, in right corner, left corner, top, middle, wherever you look, then we call such reactors as well mixed reactors. Of course, you have to have some physical provision inside the reactor to achieve these conditions, and one good way of doing that is having an impeller. That is, you have a stirrer mounted on some shaft which is connected to a power source, and you turn this shaft so that impeller rotates and it causes uniform mixing. I should also point out that there are various different ways of achieving mixing, if not uniform, at least partially, but we will talk about them when we talk about some special reactors towards the end of this course. So, we have stir tank reactors, and that is one extreme where all contents are uniformly mixed. The other extreme of flow condition is no mixing in an axial direction. And what I mean by that, let us consider a reactor, and we consider a tubular reactor, but it need not be tubular, it could be any other reactor. So, let us say that this is our reactor. Let me make this little darker. So, this is our reactor, let us say, and there is an entry point, everything we denote with subscript O, and there is a exit point. Now, in this tubular reactor there are two directions, one is the axial direction and other is the radial direction. The axial direction is the direction of the flow. So, material is flowing in from this entry point up to the exit point. So, in a plug flow reactor, it is as good as saying that liquid moves like a plug. So, imagine a thin plate or thin planar fluid, it enters into the reactor. So, we have let us say one thin plane over here, then following this another fluid element moves in, then we have yet another fluid plane moving in, and these fluid elements in this axial plane, in this plane, they do not interact with each other. So, for example, in this pictorial cartoon, these blue and green fluids do not mix with each other, they continuously move from this particular end to the exit of the reactor. So, that is to say that there is no axial mixing. So, the concentrations or fluid properties or reacting mixture properties, be it temperature or any other property, is continuously changing as we are moving along the direction of the flow, and this is what is an ideal plug flow reactor. But I should also point out that in case of plug flow, there is a complete mixing along the radial direction. Along the radial direction, there is a complete mixing. What it means is that if you look at this particular plane, then the fluid properties at this radial point, this, they are all same, and so is the case in case of green fluid. So, along the radial plane, there is a complete mixing. So, properties are uniform, but along the axial flow direction, there is no mixing of fluids, and this is what is the ideal flow behavior. And we considered the mass balance for this in the last class, and it worked out to be dFj dt equal to Rg. Let us rework this mass balance once again, so that we follow this development clearly. So, let us say that we have our reactor, and in this particular case what we are going to say is the reactor volume at the entry point is V is equal to 0, and reactor volume at the exit point is some VR. Now, let us consider a small element of this reactor at some location V equal to V and V equal to V plus delta V. Okay. Remember, along this axial direction properties are changing, but along radial direction properties are uniform. That is what our plug flow reactor is. So, now let us write down our mass balance equation for this particular reactor, saying that the concentration of the species which enters at this particular plane of a given species is Cj, and let us consider a small volume delta V and small time interval delta t. So, what happens in this particular segment? There is first of all accumulation. The mass balance is same as before, that is accumulation is in minus out plus generated. So, there is a accumulation. So, let us say that concentration at time t plus delta t minus concentration at time t multiplied by the volume of this element is how much the mass has accumulated in this small element delta V. Now, this has accumulated as a result of three different things, as I just now said. So, this is equal to, the concentration is Cj prime. Let us say that V is the volumetric flow rate, small v is the volumetric flow rate coming in, going out. So, V into Cj is the rate at which the moles are coming in. Recall that V into Cj, or if you do not like V into Cj, let us keep it as in terms of our earlier notation of Fj. That is the number of moles that are coming in at this particular volume, minus the flow rate at that is going out. So, in minus out, let me write it more clearly, V plus delta V, and this in small time interval delta t. So, this is how much has coming. Remember, we are writing balance for mass. So, everything has to be in terms of moles. So, this is what is coming in Fj at volume V minus Fj at V plus delta V into time interval delta t, that short time interval, is what is coming in and out, plus let us say the rate of change of generation of species is Rj. So, Rj into delta V into delta t is how much moles of J has been generated in this interval. Once again we have a simple mass balance, accumulation, in, out plus generation. So, now if we divide this whole quantity by delta V delta t and take limit as delta V goes to 0, delta t goes to 0, this mass balance equation now becomes del t of Cj, okay, divide by delta V delta t. So, and take limits equal to minus del Fj del V plus Rj. So, this is our unsteady state mass balance equation for a plug flow reactor, ideal plug flow reactor, that is the accumulation, the change of moles plus in and out plus generated. How do we go from this equation to this equation? If we say that we are looking at steady state, if we are looking at steady state, then del t of Cj, this term drops out, we have only these two terms. So, if we now rearrange them, we get dFj dV equal to Rj. That is our mass balance equation for a plug flow reactor. Now, there are few points which I want to mention while we are at mass balance equation for plug flow reactor, and this is the following. Now, remember, particularly if we are looking at a situation which involves a gas phase reaction and a gas phase reaction in which there is a change in number of moles, and this requires some consideration. For example, we had this reaction of ethane undergoing dehydrogenation to ethylene plus H2. We had earlier spent some time on how we calculate the flow rates and so on, or how they are dependent on temperature and pressure and so on, but let us reiterate this example once again and how it affects the design equation for a plug flow reactor. Now, what is happening here is 1 mole is giving rise to 2 moles. So, without going into details, we have delta, change in number of moles, then epsilon as delta y10, that is initial moles, all these things we had considered earlier. So, I am not going to repeat once again, but the idea is the following. Now, if you remember our discussion on kinetics, we said that Rj is a function of concentration of the species and temperature. Rj is a function of concentration of the species and temperature. This mass balance equation does not have concentration in it. Remember, the mass balance is on mass, that is on moles. So, how do we now relate these two? So, we know by our definition Fj by volumetric flow rate is our concentration Cj. So, there are two ways of relating this condition. One is you put this value of Cj in this rate expression. So, Rj now becomes function of Fj's. So, how do we link these two equations? Cj can be expressed in terms of Fj by V. So, plug that into this rate expression. So, we have dFj dV as equal to Rj which is, if we plug it for Cj, we have Fj by V, volumetric flow rate. So, that in such case we now have the mass balance equations which are consistent. But there is one more thing that we need to worry about, particularly when you have change in number of moles. Recall that we have our equation of state. If we say we follow ideal gas law, then P into volumetric flow rate is Ft into RT, and we can write the same thing at inlet conditions. And this now has flow rate Ft, and flow rate Ft is nothing but summation Fj. So, the flow rate, molar flow rate Fj not only appears over here as Fj, but also in the volumetric flow rate. So, all this will have to be considered together if we have a reaction in which there is a change in number of moles. So, this is one way. Let me recap. Our mass balance equation is dFj dV equal to Rj. Rate of generation of species J is a function of concentration, which is now expressed as Fj by V, and V in turn is dependent on the molar flow rates Ft, which has also Fj in it, and therefore, this completes the discussion. The second approach of dealing with this is as follows. We work with concentrations, that is, leave Rj as a function of Rj as a function of Cj and T, and instead express Fj as volumetric flow rate times Cj, and then write this equation as now. I will also bring your attention to a more common form which you might have seen earlier, that this is our now mass balance equation. This mass balance equation can be further simplified, and what are the conditions under which it can be further simplified? The conditions are as follows. If and only if the volumetric flow rate is not changing along the axial direction, that is, V is constant. That's condition 1. Then the diameter of this tubular reactor is constant. That means cross sectional area is constant, and mind you, that is not necessary. We may have reactors which will look something like this, where the diameter changes along the axial direction of flow. There are situations where reactors look something like this. So, we are not considering those reactors. So, if diameter is constant, as is the assumption that we have made, then the volume V is nothing but the cross section area A into whatever distance along the axial direction that we have travelled. Let us say that this V corresponds to axial direction of Z, and this is Z plus dZ. So, this is A into Z. So, if that is the case, then we can simplify this mass balance equation further. What is that simplification? V is constant, so we can take out V from this mass balance equation common outside. So, we have V, and instead of dV we will put A dou Z or of Cj equal to Rj. What is V? V is the volumetric flow rate divided by the cross section area. So, that is nothing but the velocity, the superficial velocity of the fluid in the reactor, and in that case we get our mass balance equation, which simplifies to U dC dZ equal to Rj. This is the equation which you have probably seen as a design equation earlier, but this equation is applicable only under specific case. The general mass balance equation is this particular form, dFj dV equal to Rj, which under the conditions that volumetric flow rate is constant through the entire reactor, that means there are no change in number of moles for a gaseous reaction, or if it is a liquid phase reaction, that is a reasonable assumption. Both these things boil down to constant density along the length of the reactor, and under those conditions plus the radius of the or the diameter of the tubular reactor is constant along the flow direction, then we get our mass balance equation, which looks U equal to dC dZ equal U dC dZ equal to Rj. So, now let us go back to our mass balance equation for stirred tank reactor and that for earlier we had seen that this is our mass balance equation for a well mixed continuous stirred tank reactor. The volume of the reactor equal to Fj0 minus Fj divided by minus Rj, and this is our mass balance equation for plug flow reactor, dFj dV equal to Rj. Now, one question that we may want to ask ourselves is, how does these two reactors compare with each other when it comes to performance of this reactor for certain chemical reactions, when reactions are taking place. So, let us consider a simple example of reaction A1 going to products. Okay, I am considering simple reaction A1 going to products, and for this particular reaction we can write. So, this is a simple reaction in a single reactant. So, my R1, that is the rate of generation of species 1, which is nothing but nu j into R, if R is the rate of this reaction. So, R is the rate of this reaction times the stoichiometric coefficient, and for this particular example, nu j or nu 1 is minus 1. So, R1 is minus R. So, if we consider this and our assumption that V is constant, cross sectional area is constant, then by writing F1 as volumetric flow rate times C1 and the cross sectional area A being constant. Remember our design equation D, or under this simplifying condition our design equation was u dc1 dr equal dz equal to r1. So, you substitute r1 as minus r and we normalize this by or rather rearrange this. So, take dz on one side, bring r1 and do the rearrangement. We will get if we rearrange this, we will get C10 to C1 dc1 dc1 divided by r or 1 over r dc1 equal to L by U. L is the length of our tubular reactor, U is the superficial velocity. So, this is in centimeters divided by centimeters per second, and this is nothing but the residence time in the reactor tau. So, that is how long on an average the reacting fluid has spent in the reactor from its entry point to the exit point. So, this has units of time. So, this is we call this as residence time. So, we get our mass balance equation, which for a plug flow reactor for this reaction A1 going to products under this simplifying assumptions as tau equal to C1 from the integral of 1 over r dc1, limits being C10 to C1. Now, if we do the same simplifications for a mass balance on stirred tank reactor, we get this particular design equation. This is for stirred tank reactor CSTR as we refer to it. This is for plug flow reactor or PFR. So, these are two mass balance equations, and we would like to see which of these two reactors give you better performance. Now, what is a better performance? There are two ways of looking at better performance. One is we say that our reactor length and velocities are fixed. It means we have the same residence time in a plug flow reactor and stirred tank reactor. Which of these two reactors give us higher conversion of A1? So, that is one way of comparing, and whichever gives higher conversion, that is a better of the two reactors. The other way of comparing these two would be, we say that we want certain conversion of A1, that is we are going to design our reactor for 90% conversion of A1. Then whichever of the two reactor achieves this 90% conversion with a smaller residence time will be the better of the two reactors. It's two different ways of looking at the same thing, whether a stirred tank reactor is better than plug flow reactor or vice versa. But let us look at how do we compare this, and of course, one can put in some kinetics, compute some numbers and so on, but let us try to first get a feel in a graphical way of how these two reactors can be compared. To do that, we need certain kinetics, and what we see here in this particular plot is the on x axis or rather on y axis we have rate as a function of concentration of C1, and we are going to assume that rate follows a power law kinetics. So, we have R equal to K into C1 raised to n. On the x axis, instead of plotting this rate as a function of C1, I have plotted it as a function of C10 minus C1, and the reason for this will become apparent when we go to the next slide. But for time being, let us take it that this is a function of C1, and what we see different colored lines are for different values of n, starting with n equal to -1 to n equal to 0, 1, 2 and so on. Now, let us start with the simplest case that we know, that is n equal to 1. Now, we know for r equal to Kc1, rate versus C1 is a simple straight line, right, that is a linear law. Now, how does this get converted into this violet line when we plot C1 minus C1 0? What is this particular point? This is a point when C1 minus C1 0 is 0. That means, this is C1 equal to C1 0. So, this is a point in our regular curve, this is that point rate equal at C1 equal to C1 0, which is this particular point. And as on this plot of C1 minus C1 0, as we are travelling here, what is happening at this particular point? This is when C1 0 minus C1 is equal to some value of C1 0, that means this is a point C1 0 equal to 0. So, that is this particular point. So, as we go from concentration of 0 to C1 0, the rate increases, but the same thing is happening as we are going from concentration of C1 equal to 0 in this bigger plot to C1 equal to C1 0, the rate is increasing along this violet line, right. So, this is the same rate plot, but slightly in a different manner. In the similar manner, we can plot for n equal to -1, 0, 0 where rate is independent of concentration, 1 and 2. This is the blue line is for n equal to 2. So, Kc1 square, Kc1, K and Kc1 raised to -1. So, now let us try to compare this two reactors by looking at this particular plot. Again, going back to our design equation, this is the design equation for CSTR and this is a design equation for plug flow reactor. Now, firstly we notice in both these design equations there is 1 over R, here 1 over R as well as over here. So, instead of plotting R, the same plot now I have converted into 1 over R on the y axis and versus C1 0 minus C1 on the x axis. Now, let us look at what is the performance of these two reactors. Let us take the case of n equal to 1. Okay. So, this violet line. Now, you know what is integral 1 over R dC1 from C1 0 to C1? Where is our C1 0? Our C1 0 is over here, C1 equal to C1 0 is over here and some value of C1, let us say this particular point. So, what is this integral? This integral is nothing but the area under the curve of this violet line at value. So, all this area under the curve that is the area of this integral or that is the value of this integral. So, what is this shaded area now? This shaded area is nothing but the residence time required for plug flow reactor. Let us look at what happens when we have a stir tank reactor. For a stir tank reactor, for a given value of CSTR, for a given value of C1, this is the value of 1 over R, and what is this residence time is 1 over R multiplied by C10 minus C1. So, now for a stirred tank reactor, this particular value, which is nothing but 1 over R at C1 multiplied by C10 minus C1. So, this area of this rectangle is now the residence time for CSTR. Once again, for plug flow reactor, the area under the curve for this particular curve of 1 over R versus C10 minus C1, area under the curve is the residence time. For stirred tank reactor, area of this rectangle is the residence time for stirred tank reactor. So, let us come to our design problem. Let us come to our design problem of, let us say that I want certain value of C1 at the exit of my reactor, this particular value. Okay. What is the reactor, which reactor gives me minimum residence time, and that would be the better of the two reactors. So, it is clear from this representation that plug flow reactor gives us lower residence time compared to the stirred tank reactor. So, for a reaction which is first order kinetics R equal to Kc1, my plug flow reactor results into lower residence time as compared to a stirred tank reactor for achieving the same degree of conversion. Now, this graphically this is all fine, but what is actually happening? Why is this happening? Let us try to understand it in a qualitative sense as well. Remember, in a stirred tank reactor, our inlet concentration is C10, our exit concentration is C1, and because of mixing conditions, the concentration inside the reactor is also C1. So, what happens in a stirred tank reactor? The concentration value decreases instantaneously, that is, as soon as it enters the reactor, concentration drops down from C10 to C1, and hence the rate of reaction also instantaneously drops down from that which one would have achieved at inlet condition to whatever is the exit condition. Okay. Let us compare that with what is happening in the plug flow reactor. In a plug flow reactor, what is happening to my concentration? My concentration is C10 over here at the entry point, and it is gradually decreasing. It is gradually decreasing to a value C1 along the length of the reactor. In a stirred tank reactor, from C10 to C1 is instantaneous, because as soon as the fluid element enters the reactor, it mixes uniformly with whatever is there inside the reactor, concentration drops down from C10 to C1. Whereas, in this particular case, concentration drops down more uniformly. Now, what happens to the rate? The rate also drops down instantaneously in the stirred tank reactor. It drops down more gradually in a plug flow reactor. So, in a plug flow reactor, reactions are occurring at a rate higher than that at the exit for the entire duration of the reactor. And therefore, now you can imagine, if rates of reaction are higher in a plug flow reactor, the corresponding residence time would be lower, because reaction rates are higher, it would take lower residence time to achieve the same degree of conversion. Hence, for a first order reaction, the plug flow reactor is better than the stirred tank reactor. Whatever argument we put forth right now can be also turned around and said that if the residence times are same in stirred tank reactor and plug flow reactor, we would get higher conversion in a plug flow reactor as compared to a stirred tank reactor. But is it always the case? No, we will go back to our example and see that need not always be the case. What we see here with this orange line, and let me magnify it so that it is clear. This orange line over here, this particular line, when n is equal to -1. So, now our kinetics is R equal to K C raised to minus C1 raised to -1 or K by C1. For this, the plot of 1 over R looks something like this. Now, remember our design equations are the same, they do not depend on the kinetics of the process. The performance of the reactor depends on the kinetics of the process, but the reactor design equations per se are not dependent on the kinetics of the process. So, they are the same. That means, the residence time for a plug flow reactor is area under the curve, for stirred tank reactor it is the area of the rectangle. So, let us look at what is the residence time for this particular reaction, that is K C1 raised to -1 when n is -1, n is -1, what is the residence time? So, let us say that this is the C1 that we are interested in, then the residence time would be all this area under the curve for plug flow reactor. Now, what about stirred tank reactor? For stirred tank reactor, it is the area of the rectangle, but which rectangle now? This is 1 over R at C1 multiplied by C1 0 minus C1. So, area of this rectangle shown in the blue line is the residence time in a stirred tank reactor. So, this blue is residence time for stirred tank reactor. And now, what do we see? We see now exactly the opposite phenomena, that is area under the curve is larger than the area of the rectangle, which implies that the residence time for stirred tank reactor is now lower than the residence time for a plug flow reactor. Why did this happen? This happened because the kinetics was of this kind. Again, qualitatively we can explain it as follows. Stirred tank reactor, because of its assumption of well mixed reactor, the concentrations drop down to a lower value instantaneously, whereas the concentration decrease from the inlet to the exit in a plug flow reactor is more gradual. And this aspect is independent of the kinetics of the process. But look at the kinetics now. If concentrations are low, according to this kinetics R equal to 1 over K over C1, if concentration is low, the rate is high. So, now we are getting higher rates in the stirred tank reactor because concentrations are low, whereas concentrations are relatively higher in a plug flow reactor as we move from entry point to the exit point, and hence the reaction rates are little lower, because higher the value of C1, lower is the rate of the reaction. Or in other words, now the performance of CSTR is better than plug flow reactor. We can now examine all other kinetics and see what happens. So, for example, we saw that for this n equal to 1, PFR, tau PFR is less than tau CSTR, or in other words, plug flow reactor is better than stirred tank reactor. What about n equal to 2? N equal to 2. For n equal to 2, we see that qualitatively behavior is same, that is 1 over R versus C10 minus C1 is increasing, is also increasing. So, we can expect for n equal to 2, this will be the case. What about n equal to 0? The flat line. Now, if the curve is flat, the area under the curve and area of rectangle will be same, or in other words, tau PFR is same as tau CSTR. That is, both plug flow reactor and stirred tank reactor will perform equally well. For n less than 0, 1 over R versus C1 minus C10 is a decreasing point. So, what happens for this particular reactor? Tau CSTR is less than tau plug flow reactor, or residence time in the plug flow reactor. So, CSTR is better than plug flow reactor. So, to recap, for all values of n which are greater than 0, that means the rate of reaction increases as concentration increases, in which manner, whether it is a linear or non-linear is immaterial, the plug flow reactor will be better than a CSTR. For those reactions where rate is independent of concentration, the plug flow reactor and CSTR both perform equally well, and this is to be expected, because the concentration variation does not change the rate of reaction. So, whether it drops down instantaneously or it decreases gradually, both are same as far as performance is concerned. But those reactions for which the rate increases as concentration decreases, then CSTR is a better reactor than plug flow reactor. So, before we close for the day, this is just a illustrative slide. We talked about these residence times. So, this plot over here taken from a text from Engineering of Chemical Reactions by Lanny Schmidt. This shows on the y axis the temperature, on x axis the residence time, and various reactions are noted over here. I will start with, even though you are not able to read probably this, let me say that ammonia oxidation reaction, for example, which is shown here, takes place at around 800 degrees centigrade, and the residence time is of the order of magnitude 10 raised to minus 3 seconds. So is the synthesis gas reaction, I mean similar order of magnitudes. So, higher temperature, lower residence time, because if you look at this plot, even though it is not falling on a single line, it is obvious that the trend is in this particular band, that is, higher the temperature, lower is the residence time, and as the temperature of operations decreases, the residence time increases. For example, a case of bacterial fermentations. Bacterial fermentations have residence times of hours, days sometimes, and these are carried out at 30 degrees. So, on this extreme we have 30 degrees or up to 40, and residence times which are 10 raised to 5, 10 raised to 6 seconds. You can work it out in hours and so on. So, as temperatures are higher, residence times are lower, as temperatures are lower, residence times are higher. With this, we will come to the conclusion of our design equations. So, essentially what we saw in this particular lecture was how to do a mole balance on a reactor, and we considered only ideal reactors. Ideality dependent on the flow pattern inside the reactor, that is whether it is a well mixed reactor or whether it is a no mixing in the axial direction or a plug flow reactor. We have different kinds of reactor behaviors. We also have different types of reactor operations, batch, continuous. We will come back to semi batch reactors which fall in between little later on. Then we saw the design equations for all these reactors and expressed for simplified case residence time tau, which is can be expressed in ratio of length of reactor to the velocity or volume of the reactor to volumetric flow rate, and compared the performance of stirred tank reactor and plug flow reactor. With this, we will come to the conclusion of our review of undergraduate material, and from the next session we will start discussing about complex reactions, some basic aspects of complex reactions and few examples of complex reactions before we go on to heterogeneous reactions. Thank you.